Imagine generating electricity straight from waste heat. No fuel, no smoke, no moving parts. Not just for households, but even for industrial operations. This isn't science fiction. It's the result of a groundbreaking innovation in thermoelectric energy developed by researchers at the Technical University of Vienna. They've created a new kind of thermoelectric generator, one that can turn excess heat from the environment directly into usable electricity. No steam turbines, no combustion. Just heat transformed into power. At the center of this development is something called a Kagome metal. This material isn't your average metal. It's structured at the atomic level in a pattern resembling a star, based on a traditional Japanese basket weaving design. It might sound decorative, but this structure changes everything about how electricity flows. But before we get into the modern innovation, let's go back nearly 200 years. The principle this device relies on is called the Seebeck Effect, discovered in 1821 by physicist Thomas Johann Seebeck. The funny part, he didn't even know what he had found. He connected two different metals into a closed loop and exposed the junctions to different temperatures. Surprisingly, when he placed a magnetic needle near the setup, it moved, apparently without any external magnetic field. He assumed the temperature itself created magnetism. That turned out to be wrong, but what he had actually discovered was the first thermoelectric generator. What happened was this. The temperature difference between the metals created a voltage. That voltage pushed an electric current through the circuit. And that current, like any current, created a magnetic field, enough to move the needle. Here's how it works on a deeper level. In metals, electrons, negatively charged particles, are free to move around. This is why metals conduct electricity so well, but their movement depends on temperature. In a metal exposed to heat on one side and cold on the other, electrons on the hot side move faster. That imbalance causes electrons to drift toward the colder end, creating a charge difference, a voltage. Sounds simple, right? But there's a problem. In most metals, both negative and positive charge carriers move freely, and crucially, they move at nearly the same speed. So the charges cancel each other out. The result? Weak voltage. Weak current. Not useful for energy generation. That's why thermoelectric metals have traditionally been inefficient. Their ZT value, a measure of how effectively a material converts heat to electricity, has always been low. Until now. This is where Kagome metals flip the script. By organizing atoms in a specific Kagome pattern, built from triangles and hexagons, the researchers discovered they could trap some types of charge carriers while allowing others to flow freely. It's like designing a two-lane highway where traffic is deliberately jammed on one side, but flows freely on the other. This creates a directional charge movement, exactly what you want if you're trying to generate electricity from temperature differences. At first, this breakthrough was achieved using a costly combination of nickel and gold. But now, the same structure has been replicated with a much cheaper material, a combination of nickel and indium. This metal composite maintains the necessary atomic structure while avoiding expensive components. What's revolutionary here is that this metal behaves almost like a semiconductor, but without actually being one. Inside this metallic material, negative charges can flow almost without resistance, while positive charges are effectively immobilized. That asymmetry creates a steady voltage in response to heat, a direct electrical output without any moving parts. This is a paradigm shift in thermoelectric technology. Unlike traditional generators, which require spinning turbines, maintenance, and moving components, thermoelectric generators are solid-state devices. They don't wear out easily. No gears, no lubrication, no noise. And because they're compact, they can be integrated almost anywhere. Think of portable coolers, car exhaust systems, industrial ovens, chimneys, or even space probes. Any environment where excess heat exists now becomes a potential power source. And here's the kicker. These new Kagome metal generators work efficiently at room temperature, between 0 and 27 degrees Celsius. That's unprecedented. Until now, the main limitation of thermoelectric generators was that they only performed well at high temperatures. But with this development, We're looking at devices that can function under everyday conditions, unlocking a whole new level of practical use. Even more exciting is the potential for integration with heat storage systems, like sand batteries, which store excess energy as heat. Traditionally, these systems have been used to deliver heat back into homes or water systems. But now they could also feed thermoelectric generators, converting stored heat back into electricity. That means a loop of energy reuse. Solar panels generate excess power, heat is stored, and then converted back into electricity when needed, all with no moving parts and no emissions. Of course, this technology is still in the experimental phase. There are hurdles before we'll see it in homes and industries worldwide. But this is no small step. After decades of stagnation in thermoelectric research, this is one of the most promising breakthroughs to date. And perhaps most importantly, this progress is happening in Europe, a region often considered behind in energy tech. But this development shows otherwise. It's proof that major innovations are still being made, and they have the power to reshape how we think about sustainable energy. Thermoelectric generators powered by Kagome metals might just be the key to turning the waste heat all around us into clean, quiet electricity. And this time, the future really is heating up.